So let's take a look here at example number 1. I want to find the flux of this vector field across the unit sphere x squared plus y squared plus z squared equals 1. Okay, notice that this is a flux question. And so this is reminiscent of the questions that we talked about in the last section. Well, I'm going to go ahead here and quickly see how I can begin to tackle this question without having to directly compute the flux. I'm going to try to use the divergence theorem to help us. If I take a look at what we have here, I can see that if I wanted my sphere to have to meet the conditions of the surface that we need to work with up here, I want to have G be a solid whose surface sigma is oriented outward. So to orient my surface outward, I need to go ahead and imagine normal vectors that come out of it in this direction, right? Moving outward, as opposed to in towards the center of the sphere. So I'll say here that we can definitely assume the sphere has positive orientation. Remember, on a closed surface, a positive orientation means pointing outward from that surface. So we want to find the double integral over sigma, which again is going to be represented as the boundary of this unit sphere, for f dotted with n, which represents my positive orientations. Again, here I'll say where sigma is the boundary of the sphere, oriented positively. Okay, so that's what I want to find. But again, this might take a lot of work because, as we might recall, we did a problem very similar to this in the last section where we computed flux, and we had to go ahead and start setting up a parameterization of this surface using spherical coordinates, and it was a whole big deal. But instead here, I'll notice I have a closed surface. It's outward oriented. I have F, whose a vector field, and the components have continuous partial derivatives. That's easy because these are all polynomials. Their derivatives are going to definitely end up as continuous functions. And so if I go ahead and use my divergence theorem, I can really help compute this flux integral by instead considering what the solid G is and what the divergence of F is. So let's see what we come up with. So I'll say here, we see that sigma is the boundary of a solid G, which is again a bunch of x, y, z points, but I can easily tell what creates the restrictions for those points. It's got to be the case that these points are either less than, these x squared plus y squared plus z squared is less than or equal to 1. If it's equal to 1, that would put a point on the sphere, and if it was less than 1, it would put a point to the inside of the sphere. So this is the solid that I'm working with. But then I can see that the divergence theorem tells us that to compute this flux integral, I could instead compute a triple integral over that G with divergence of F being calculated in as the integrand. Now, of course, that's not too difficult to go ahead and do because we saw in earlier videos in this section that the divergence of F is very simple to calculate. I would just go to each one of the components and take the partials with respect to x, then y, and then z. So notice in this case, I'm just going to be left with 0, not comma, but 0 plus 1 plus 0. Partial with respect to x is 0, partial with respect to y is 1, partial with respect to x is 0. So really what I have here is a triple integral over G of just 1 dV. Oh, and you might recall, if I do a triple integral over G, With just a 1 in there, do you remember what this represents? Well, this represents the volume of G. So by itself right now, this is still a fairly difficult integral to compute. I'd have to set up bounds to try to work with this, probably use spherical coordinates to help. But if this is just going to represent the volume of that solid, and I already know that's the solid that's in the shape of a sphere and has radius 1, I already know the formula for that is 4 pi over 3r cubed. So like, if r is a value of 1, that's just going to be 4 pi over 3. Boom! I'm done. And I bet if you were to take a look back at section 5.6, I believe it was example number 1, you would see that we got the exact same answer. What the divergence theorem allowed us to do was to, instead of computing this flux integral directly, compute it by first setting up this triple integral, which has the same answer. In the next video, we'll take a look at how this works with some other vector fields and other sorts of functions.